Becoming part of an international community of physics teachers has been such a rewarding experience. It is my pleasure to present to you what I have learned and how this has impacted my outlook on physics education moving forward. This image sums up not only the idea of collaboration that CERN embodies, but also the dedication of all the wonderful educators I met at HST 2024. Philip Bechtold bought this guitar on our second day and he became our evening entertainer. Every participant and presenter signed his guitar throughout our 2 weeks together. It is a symbol of what we accomplished together and what we can do as we move forward together. I thank you all for supporting this program and owe you a debt of gratitude. I listened to world class presenters, saw world class technology, learned about cutting edge research in particle physics and beyond, and it opened my eyes to the possibilities in science and education. I now have a team of international colleagues who are all passionate about physics education and want to share this passion with our students. Thank you to the Canadian Association of Physicists, the CAP Foundation, Triumph, Perimeter Institute, engineers and geoscientists of British Columbia, Snow Lab, and the Canadian Light Source for sponsoring the CAP Award for Excellence in Teaching High School CEGEP Physics and encouraging and promoting physics education in high school. Lastly, thank you to the Perimeter Institute and the Institute for Particle Physics who provided supplemental sponsorship for my trip to CERN. During this presentation, I will walk through the agenda from the 2 week program and highlight what I experienced and learned. I will also give some of my own opinions and insights on the program, and by highlighting curriculum links locally and globally, I hope to shed some light on education here in Canada compared to other countries. This has directed the next steps for me professionally in terms of how I plan to incorporate this into my own teaching and how to expand and share what I've experienced with others. Lastly, I will talk about not only what are the future plans for CERN, but also what next steps we should take to ensure our students and the scientific community at large can participate with the global network at CERN. The main instruction for my 2 week program came in the form of lectures, the first being the famous John Ellis. He is the second most cited theoretical physicist of all time, and he talked about the natural curiosity of humans and linked the big questions in nature to the work of particle physicists at CERN. Our job is to ask and answer these big questions. Mike Lamont is the current director for accelerators and technology and has a long history at CERN after joining them in '89 as a PhD fellow. He talked about the history and evolution of particle accelerators from linear to circular and how they work. He gave an in-depth presentation on the advanced engineering required to accelerate and collide two beams of trillions of protons traveling at 99.9999991% the speed of light, including how to cool the magnets, how to control the beams, and how to accelerate the proton bundles. Next, we heard from Claire Lee, an absolute breath of fresh air, and she showed me a whole new way of looking at science and physics. I've watched a few YouTube videos of her since my return home and hope to expose my students to her when I return to the classroom. Claire talked to us about how we can tell information about particles based on their interactions since we cannot see them. Fun fact, if you extract all the empty space from all the atoms that make up every human on the planet, we would all fit in a teaspoon. Louis Castillo encouraged us to motivate students to aim high. Considering the massive undertaking of the search for the Higgs boson, $9 billion, 20 countries, 200 institutions, and 30 years searching, and all of the discoveries and spin-offs that have resulted from the Large Hadron Collider. Without the Higgs boson, there would be no atoms, no stars, no planets, and no life as we know it. And on July 4th, 2012, both ATLAS and CMS collaborations independently confirmed its discovery. Fun fact for students, we are all stardusts. Our next presentation was about engineering at CERN by Raymond Vaness, and he talked about how theory meets practice and reality. The physics specifications that the engineers were given was to build an experimental beam pipe out of nothing that contains nothing, held up by nothing. They did it using beryllium and created an essential deep space vacuum beam pipe with 10 to the negative 11 to 10 to the negative 10 millibars of pressure. 41% of people who work at CERN are engineers, while 35% are technicians, and only 3% are research physicists. Although CERN is a particle physics facility, most of what they do is engineering in order to produce the most amazing, complex, and beautiful devices. Interesting fact, while digging out the CMS cavern, they found an underground river that they had to freeze and redirect. One can barely fathom the technique and skill that goes into pulling off such an engineering feat as running the Large Hadron Collider. George Trad called up the live stream of the LHC, and at the time there were 2.28 times 10 to the 14 protons in beam 1 and 2.34 times 10 to the 14 protons in beam 2. While we were watching, the LHC shut down because one of the magnets wasn't drawing enough current. He spoke to us about the production side of things and what happens in the day-to-day life of those people who are working to get the LHC filled up, particles accelerated, and ready to collide. As the lead organizer for our HST program, Jeff Wiener took an opportunity partway through our lectures and tours to give us some perspective on how to relay this information to students. He cautioned us about choosing accurate and appropriate language and made us aware of a number of open source articles and activities that are appropriate for the classroom. Our next speaker gave 2 presentations. Frederick van der Wecken is an off-the-cuff speaker who was chaotic and raw, planted there to challenge our view of how things go. He spoke twice by design, once for shock value, and another to really get us thinking past our experiences to consider the actual mathematics behind the experiments. From a student perspective, Frederick's path that led him to CERN was a bumpy one, filled with many paths, such as art, philosophy, music, and physics. He actually failed physics in high school and in his first year university. He still ended up with a master's in string theory and a PhD in quantum field theory, and currently works on beam dynamics at the LHC. His talks to us shone light on the fact that our language and minds are flawed and limited, and all the while we are talking about particles whereas a particle doesn't exist in the technical and mathematical sense. He talked instead about the interaction radius and what is happening in mathematical terms since our language is lacking. In his second talk, he taught us about Feynman diagrams as mathematical tools for bookkeeping and communication, recognizing their limitations as well. A way to incorporate this into the classroom may be an introduction to models or as an example of conservation laws. As the lead person responsible for the compact muon solenoid, Dave talked to us about his 30-year career with the CMS collaboration. It took 20 years to build, is twice the weight of the Eiffel Tower at 14,000 tons, and contains 5 main detecting layers, an easy design to explain to students. With 6,008 active members from 57 countries, CMS shows how collaboration is key in scientific developments and discoveries. The CMS detector has only taken about 3% of the planned amount of data to date, and with over 1,100 papers published using the CMS data, there's so much more to learn about such things as dark matter, dark energy, antimatter, and mass itself. The first ever computers at CERN were 2 British ladies hired on secondment. Tim Smith led us through the evolution of computing at CERN, from processing bubble chamber images by hand to vacuum tubes to supercomputers to data centers. The World Wide Web was invented at CERN by Tim Berners-Lee in response to information management needs, a scientific invention that benefits the entire world. With 150 million sensors generating data 40 million times per second, there is petabytes of data produced at the LHC each second. Choosing what data to keep and how to store it long term requires innovative solutions. Tim cautioned us about the concentration of power moving from countries to companies, as we are currently in the misinformation age. Zenodo is being built to regain trust in science. CERN believes in open source, universal access to information. Companies, however, do not. Perhaps the most uplifting and passionate of all speakers, Manjit spoke of her passion to have equal access to medical technologies. Both Tim and Manjit showed that fundamental science research continues to be the main inspiration for revolutionary ideas, and innovation is what fosters technological advancements that benefit society as a whole. Particle detection initially paved the path for X ray technology that is commonplace today. Furthermore, the work at the LHC has led to medical applications like CT scans, PET scans, and MRIs. Radiation therapy is used to treat about 50% of cancer patients. Particle therapy has advanced since its first use in 1954, and we are now using protons and carbon ions to treat the tumor and only the tumor, saving healthy tissue and seeing amazing results. The first patient treated with flash proton therapy was in November of 2020, and CERN is in collaboration to build a very high energy electron radiotherapy machine in 2025 to start clinical trials in 2027. Valerie Demock is a theoretical physicist who studies collisions at CERN, which reproduce conditions 10 to the negative 17 to 10 to the negative 10 seconds after the Big Bang. By studying the smallest distances at the highest energies, they are attempting to describe the formation of the universe. Although we currently know what's happening on Earth, we only know 5% of what's happening in the universe. Cosmic background radiation has revolutionized our understanding of the universe, but cosmologists are now looking for what gravitational waves will teach us. We have learned much about the history of the universe, but there are so many unanswered questions for current and future physicists to answer. Yota is currently doing her PhD in physics education, but worked on the Alice experiment for years as a master's student. Microseconds after the Big Bang, quarks under high temperature and pressure were not confined as they are at normal conditions, but rather were in a quark-gluon plasma. By studying its properties using the LHC, we can understand the processes during the first moments of the universe and better understand the strong interaction and predictions of quantum chromodynamics. The ALICE collaboration, a large ion collider experiment, with 2007 members from 40 countries, collides lead 208 ions about 1 month a year, and using specialized particle identification studies, the resulting hadrons from the collisions. Fun fact, the QGP, or quark-gluon plasma, only lasts for about 3 times 10 to the negative 24 seconds after the collision, so it cannot be seen directly. Antimatter was proposed by Dirac in 1930 and was first discovered in 1932 in a cloud chamber. Antimatter has all the same properties as matter, but they are opposite symmetric particles. So they have the same mass but opposite charge and spin. When quarks combined in the early universe, they formed matter and antimatter, much of which annihilated. We actually don't know why we can observe matter in the universe but have not yet found antimatter. Another question to be answered by CERN, of course. At the antimatter factory, they are creating antimatter of different types and studying it in controlled conditions to test its fundamental properties and interactions with complex systems. Marlene Turner spoke of the Advanced Proton-Driven Plasma Wakefield Acceleration Experiment, which is a new way to accelerate charged particles using plasma wakefields. Rather than having to build a huge circular particle accelerator underground, a wake is using the fields created by the motion of plasma particles, which generates much stronger electric fields as compared to RF cavities. Much of the experiments conducted at the LHC are certainly beyond the scope of what a junior high or high school student could comprehend. The beauty, however, is that the fundamentals behind all of their experiments can be linked back to basic physics principles that do connect to local curricula. For instance, within the plasma wakefield experiment, charged particles traveling close to the speed of light carry transverse electric waves, whereas longitudinal fields are needed to accelerate them. In this experiment, they use the plasma to convert the transverse field of the proton bunch into a longitudinal electric field. A wake is the only proton-driven wakefield experiment in the world. Marlene showed us some results from this research and developed experiments with the goal of designing a high quality and high energy electron accelerator. A fitting final lecturer for our session was Bernard Holzer, a senior researcher with the Beams department at CERN. Bernard has amassed almost 1,000 publications throughout his almost 40-year career at CERN. He walked us through the future high-energy frontier colliders, that is, options being explored by the European Strategy Group for what are the next steps for investing in future particle colliders. Plans are underway now for a high luminosity upgrade of the current LHC, which I'll talk about later, and other plans for high energy physics include a future circular collider to achieve higher energy collisions, linear colliders such as the International Linear Collider or the Compact Linear Collider, energy recovery linear colliders, a muon collider, and of course plasma acceleration that Marlene talked about. Bernard ended by getting us to consider open-ended questions about dark matter and energy, physics beyond the standard model, beam dynamics aspects, and technical aspects that must be considered. Perhaps the most engaging part of the 2-week experience was the opportunity to participate in site visits and hands-on learning experiences. The agenda was organized such that the site visits were dispersed throughout the lecture series, but also matched with the content presented. The now retired synchrocyclotron walked us through the early history of the first circular accelerators and the early results, and is pictured in the top right image. An interactive museum-style room complete with a historical timeline, video presentation, and light show was both impressive, concise, and informative. Our next stop was the Atlas control room, where wall-to-wall monitors and computers control the triggers, data quality, calorimeters, and various detectors inside the Atlas experiment. The picture in the bottom right is an artist's presentation of the Atlas detector painted outside the control room. The magnet test facility pictured in the top left was a much larger space, as you would imagine it would need to be. We learned all about how the magnets need to be trained by gradually changing their temperature and supercooling them over time. It takes months to train the magnets that go into the LHC, and the expansion and contraction of materials due to the cooling process requires meters of extra space. The next stop was the CERN Control Center, where the control rooms and teams of each accelerator sit so that they can communicate quickly and effectively. The room is designed in the shape of a quadrupole magnet and contains separate consoles dedicated to the Large Hadron Collider, the Super Proton Synchrotron, the Proton Synchrotron, and the technical infrastructure, respectively. The one place that I wish I could transport all of my students was Science Gateway. The world-class displays throughout Science Gateway explaining quantum mechanics, particle detectors, particle accelerators, links to cosmology, as well as art, were so interactive and informative. I could have spent days there. When my family came to see me at the end of my program, Science Gateway was our first stop and is still my children's favorite part of their trip to Switzerland. Another highlight of HST 2024 was the opportunity to go down to the CMS service cavern. Since the LHC was running while we were there, no one could go all the way down to the actual tunnel, but we were able to travel 88 meters below ground, pictured here in the bottom left. The role of engineers and technicians was never more evident than when witnessing firsthand the machinery required to run such a huge experiment. Equally as impressive was the data center, picture in the top left with wall-to-ceiling wires and computers. We walked through a history of old methods used to store data and saw how more and more data is stored on smaller and smaller devices throughout history because physical space requires it. Our tour guide for the antimatter factory conducted her personal research there, so our tour group got a passionate and personal account. The antimatter factory is the only known place in the universe that creates antimatter. Our last site visit was the Low Energy Iron Ring, or LEIR for short, where long pulses of lead ions from the LINAC-3, a linear accelerator, are transformed into short, dense bunches to inject into the LHC. Before I went to CERN, I did not consider all of the steps that need to be taken in order to get particles, or more specifically particle bunches, into the LHC traveling close to the speed of light. There are so many other experiments, devices, and stages to perform before the LHC can even be operational. It is mind blowing, to say the least. When we went to Science Gateway to explore the exhibits, our large group of delegates was divided into two groups so that half of us could become students again. The teacher in residence conducted a workshop whereby we built our own cloud chamber and made observations, pictured here at the top. They gave us tips on how to incorporate this into our own classroom with a list of materials you could purchase at home. I was beyond proud to welcome the Perimeter Institute for a full day event of teaching resources. I have been using some of the resources already, but was invigorated by the new and cross curricular resources they have developed in recent years. The picture in the bottom left shows one experimental setup that we actually collected data from during the workshop. Our final two workshops showed great ways to introduce particle physics to our younger students. We built mini Atlas and CMS detectors out of Lego, pictured here at the bottom right, and also made hovercrafts to float our Lego detectors using balloons, since air is how the massive detectors were actually moved into place at the LHC. I have presented a lot of content to you already, and I know I would overwhelm students if I attempted to cover all of the nuts and bolts of what I've learned as a physics educator. Above all, I want to highlight four key takeaways from all of the presentations and workshops I attended. CERN began after World War II with the goal of creating science for peace, where scientists work together for pure discovery and are not governed or motivated by military or other means. What began as a nuclear research mandate grew to include fundamental research in particle physics that has many connections to other areas of physics and science. All the information at CERN is open source and available, and with international communication and teamwork, none of the great discoveries of CERN would have been possible. In addition to collaboration, CERN strives to employ creative problem solvers, and this creativity is what separates people at CERN from many other places of employment. Yes, knowledge is important, but simple knowledge and facts will only get you so far. The people at CERN have been given the biggest problems in the world to tackle, and without being adaptable and creative, they would not have been able to achieve the monumental successes and discoveries that they have. The spin-off benefits from this creativity affects every human in the modern world. Thanks to advances in particle physics at CERN, we have the internet, touchscreens, and modern cancer treatment, for example. Much of the tasks set before the scientists and engineers seem impossible. Again, building a tube out of nothing that contains nothing and is held by nothing. The final takeaway from this seemingly ridiculous request is that impossible is only a mindset. Everyone at CERN is committed to learning every day and becoming better. They are resilient and hardworking, and it is humbling to witness. While at HST 2024, I was at times disappointed by the lack of preparation the students of Newfoundland and Labrador have in comparison to students from around the world. I do suspect that students in the rest of Canada are also in the same boat. As I spoke to my new colleagues and witnessed lecture after lecture, I realized that many elements of our curriculum do not explicitly contain content relevant to our current understanding of the universe. Nonetheless, when I came home, I went through all the curriculum guides from junior high through high school in order to highlight areas of our curriculum where teachers can link information studied at CERN. In as early as grade 7, students study the properties of matter and what happens when you change the temperature of matter. Why not introduce properties of superfluids, like superfluid helium? If students can learn about conductivity, it would be a natural step to let them know that superconductivity exists and applications of it. By drawing the parallel between microscopes and particle accelerators, the collisions at the LHC reproduce conditions at the beginning of the Big Bang. We need extremely high energies to probe small distances to see what we cannot see with microscopes or light. Links to this, as well as the standard model of the atom, can be made as early as grade 8 and 9 when discussing light, the origins of the universe, and the structure of the atom. In the high school curriculum, much of what happens directly at the LHC can be linked to the Physics 3204 curriculum, but students in Science 1206 can be exposed to the notion of particles accelerating when they learn about kinematics in the motion unit. Similarly, The particle collisions that take place in the LHC can be used as examples in the 1D collisions in Physics 2204. Again, a higher correlation exists between content knowledge in Physics 3204 and the basic principles behind particle accelerators. In Unit 1, two-dimensional collisions can be modeled using the particles from the LHC. Circular motion in Unit 2 is a natural link to the motion of the particle bundles as they prepare for collisions. And indeed, the strongest area of our 3204 curriculum that links to what is studied at the LHC is Unit 3, where electricity and magnetism meet. Here is a great place to introduce the engineering side of things in terms of the immense magnetic fields, the current electricity used, and the speed with which these particles accelerate due to the movement of charged particles in this magnetic field. Lastly, seeing the big picture and the cross-curricular links, as well as unanticipated spin-off benefits, are a great way to link science, technology, society, and the environment with what's happening at CERN, while developing important scientific literacy skills like questioning, experimentation, analysis, communication, teamwork, collaboration, and overall attitudes towards science. In 2020, the European Strategy for Particle Physics Update called for the community to work with educators and stakeholders to adopt the basic knowledge of elementary particles and their interactions in regular school curriculum. Some countries are farther ahead as compared to others, and the curriculum in my province and country seems to be lacking as compared to most, in particular as compared with India, Australia, England, Austria, and Belgium. Many teachers who attended HST 2024 had opportunities in their curriculum to expose students to our current understanding of particle physics, whereas there are no direct links in my curriculum. Furthermore, the mathematics curriculum in some countries, such as Italy, was far ahead of where our math curriculum currently stands. In 2022, Horvat et al. Completed a review of high school physics curriculum from 27 different countries, and in preparation for this presentation, I reviewed their results. They are consistent with what I saw at HST 2024. Of the 27 countries studied, 12 had a dedicated chapter or unit on particle physics in their formal curriculum, and 15 did not, including Canada. Topics that are missing or lacking in our formal curriculum include the study of cosmology in terms of the Big Bang, inflation, and expansion of the universe, the standard model of particle physics, fundamental interactions such as the electromagnetic force, the strong force, the weak force, and gravity. Electric charge is studied, but there is no mention of the strong charge or the weak charge. Elementary particles such as quarks and leptons. Interaction particles such as bosons and gluons. The Higgs field or the Higgs mechanism. Particle transformations. What Feynman diagrams are, what they represent, and how they are useful. The current state of antimatter research, or even what antimatter is, what a particle accelerator is, or what types are available and why you would use different types of accelerators, how particle detectors work and how they have evolved over the years and what they can tell us, the true science meets tech dilemma of how to store and analyze data from particle physics experiments, and the advancements made in particle physics over the last 50 years, as well as real-life applications of particle physics. So where does that leave me? Well, I figure as an alumni of HST 2024, it is my duty to share my experiences with others and spread CERN's mission as far as I can. When I return to my classes in the fall, I plan to infuse particle physics examples within my notes where possible, with the hopes of igniting some fruitful conversations and sparking interest in the next generation of physicists and engineers. I'm going to give a presentation to my school's STEAM club this month about what happens at the LHC. I also hope to offer age-appropriate workshops to junior high students and younger through a physics interest group that I am involved in. I currently sit on the Math Science Special Interest Council and have written an article about my experience at CERN to distribute to teachers across Newfoundland and Labrador. I plan to reach out to teachers in my province and hopefully in other areas of Canada to help them connect particle physics to their curriculum. After presenting this slideshow to you, I also plan to share it with my local university, Memorial. After hosting a workshop in the fall with the Perimeter Institute, I asked local media to come to our school and do a piece about our teacher and student workshop, and that local media coverage is all what CERN wants in terms of spreading the word to the community at large. So what's next at CERN? The LHC is nearing the end of data collection and has entered into its final phase as the current LHC shutdown is making high luminosity upgrades to the current infrastructure. The objective is to increase the integrated luminosity 10 times greater than the original design value, which will increase the rate of collisions. Rare events, such as Higgs events, can be studied in greater detail. Data collection is slated to begin by 2030. There are other energy colliders in the works, and some options for CERN and elsewhere include the Future Circular Collider study, which is ongoing, with plans to create a 91-kilometer collider underground similar to the LHC, but with a larger radius to create higher energies and therefore more collisions. The study is expected to conclude in 2025 and is currently investigating viability in terms of finances, geography, environmental impacts, design, engineering, and others. The FCC would first become an electron-positron collider and then be replaced with a hadron-hadron collider in the same tunnel, similar to how LEP was replaced by the current LHC. The Compact Linear Collider, or CLIC, is a proposed linear accelerator for CERN's accelerator complex that will collide electrons and positrons at high energies to conduct high-precision measurements of Higgs boson interactions. Construction is proposed to start by 2026, which would mean that the first beams would be ready by 2035 to launch a 25 to 30-year CLIC physics program. The International Linear Collider is another option in terms of linear accelerators, but now in northern Japan, although CLIC would operate at higher energies while still having a similar length to the International Linear Collider. Both projects have been unified under the Linear Collider Collaboration for Study and Feasibility. Other experiments are being conducted at CERN to discern the feasibility of other methods of colliding particles, including energy recovery linear colliders, where 2 or 4 linear colliders would be used in conjunction, a muon collider, and colliding particles accelerated using plasma. What are the next steps that we all can champion to make sure our students are prepared and that the public realizes the importance of fundamental research in particle physics? We all need to push for curriculum changes that ensure that our curriculum guides are living and breathing documents, that our teachers are updated in their current knowledge in the field, that our approaches to assessment and evaluation are rigorous in nature, and that we connect across relevant disciplines wherever possible. The community at large needs to be educated about physics and how it is pervasive in their daily lives. We need to learn how to motivate those that are not already motivated by this amazing subject area and all that it has done for the world. We need to learn how to be better advertisers in order to get the message across that physics research is valuable beyond the dollars and cents put into it. Lastly, we must support each other wherever possible with funding opportunities, time to learn, time to collaborate in order to share not only knowledge, but also our own resources. Thank you once again for this amazing opportunity. I will leave you now with our formal group picture and all the amazing colleagues I met during my 2 weeks at CERN. Together, we are going to change the world. Thank you. Thank you once again for this amazing opportunity. I will leave you now with our formal group picture and all the amazing colleagues I met during my 2 weeks at CERN. Together, we are going to change the world. Thank you.